I'm actually part of a hardware design group and not focused on designing novel computer vision algorithms, but we are more focused on designing efficient hardware structures to run these computer vision tasks in a very efficient way. So we're actually targeting battery-operated devices such as smartphones, smartwatches, and so on. And these are devices on which you cannot put a GPU to do the computations because they simply cannot fit into the power budget. So we basically design dedicated ASICs, in this case for ConvNets. And what we did here is high-level system analysis on a couple of benchmarks, LINET5, CipherQuick, and AlexNet, to see how we could basically improve the algorithms to save energy consumption. I think most of you are familiar with ConvNets, but from a hardware perspective, there are basically two power bottlenecks. We all know these ConvNets are very deep, there are huge amounts of data and a lot of computations, and this basically translates into high energy consumption. So that's the first bottleneck. Second bottleneck is basically the network size. So these networks are huge. You have to transfer network data from off-chip DRAM memory onto on-chip SRAM, and all these data transfers they take a lot of energy as well. So we started looking into these ConvNets algorithms and started looking for some characteristics that could help us to minimize the energy consumption. And we saw basically two important things. The first is that the CNNs actually that you don't have to run them on 32-bit floating point GPUs, but you can use much less precise number representations. And the second one is that these ConvNets are very sparse. Up to 70, 80, 90% of the data is actually zero, and this is something you can exploit in a dedicated hardware solution. So as the first thing we saw was that ConvNets have very limited precision requirements. So we did a fixed point analysis on the three benchmarks. The one on the left is LINET. It's used for digit recognition, then CipherQuick and AlexNet. And what we saw is, especially for the LINET5 one, quite striking. In these graphs, on the x-axis you see the layer number, and on the y-axis you see the number of bits needed. So for this LINET one, which is on the left, you see that for the first layer you only need 1 bit to represent your data. So this is something, if you're designing hardware, something that you can really exploit. The complexity of 1-bit multipliers, for example, is much lower than for a 32-bit floating point one. So that's one thing. And also, if you go to reduced bit width representations, you need less memory in terms of megabytes to store your networks. So this can lead to huge energy savings without actually losing accuracy. And we quantify this on the poster and in the paper as well. So the second thing we saw is that ConvNets are very sparse. This is basically due to two reasons: due to the ReLU layers that are placed in between, and also due to the reduced precision that we've discussed on the previous slide. So if you look at an example here on the right, these are some plots for AlexNet. You see that if you look at the usable range from 5 to 10 bits, that the sparsity in AlexNet is actually very high. It's up to 70 to 80% of the intermediate features are 0, and up to 10 to 30% of the weights are 0 as well. So this is also something we can exploit by doing lossless compression, for example Huffman decoding and so on. We don't have to fetch these 0 data, these data values, and we don't have to use them for computations. So if you combine all of these techniques, we can really get to very energy efficient hardware implementations. So the last thing we did in this paper was we first derived a simple energy model and then try to quantify the gains of the things we propose here. And then you see that you can really get huge gains if you can just turn in a little bit of accuracy. So for example, for the LINET5 one, which is on the left, we get a 100x gain compared to 16-bit fixed point. And for AlexNet you get a 30x relative gain compared to the 16-bit baseline. Yeah, so this was basically the analysis we used to start designing our ASICs. It's something we did before, and we designed one based on these findings, and it will hopefully be presented in June as well. So if you're interested in any of these, please join us at our poster. Yeah, thank you.